Imagine controlling the outcome of quantum processes using light. That's the essence of coherent control. By shaping the phase of laser pulses, we can actually control quantum interference phenomena. It's like tuning an instrument, but instead of music, we're orchestrating the behavior of particles at the quantum level. So why does this matter? Coherent control isn't just a cool concept, it has a ton of practical applications. For instance, in spectroscopy, it allows scientists to get more accurate measurements of molecular structures. In mass spectra, it helps identify different substances with greater precision. But wait, there's more. Coherent control is also making waves in quantum information processing. This is the backbone of quantum computers, which promise to revolutionize how we solve complex problems. By controlling quantum states precisely, we can perform computations at speeds unimaginable with classical computers. And that's not all. Laser cooling and ultracold physics use coherent control to chill particles to near absolute zero. This opens up new frontiers in studying quantum phenomena in a supercooled environment. The initial idea behind coherent control was to manage and influence the outcome of chemical reactions. Imagine having the power to determine how atoms and molecules interact. Two primary approaches were initially pursued to achieve this control. The first was in the time domain, known as the pump-dump scheme. Here, the control mechanism was the time delay between laser pulses. Think of it as setting a precise timer to orchestrate a chemical reaction. The second approach was in the frequency domain, where interfering pathways controlled by 1 and 3 photons were used. This method allowed scientists to manipulate reactions by adjusting the frequencies of the laser pulses, akin to tuning a radio to the exact right station. As these methods developed, they eventually merged with the introduction of optimal control theory. This was a game changer, providing a mathematical framework to find the best possible way to control quantum systems. Soon enough, experimental realizations followed in both the time and frequency domains. Two groundbreaking advancements accelerated the field even further. The first was the development of pulse shaping using spatial light modulators. This technology allowed for precise control over the shape and timing of laser pulses, making coherent control more accurate and versatile. The second was the concept of automatic feedback control. This innovation enabled experiments to adapt in real time based on feedback from the quantum system itself. Together, these advancements have propelled the field of coherent control to new heights, opening up endless possibilities in quantum chemistry and beyond. It's like having a magic wand that can influence the fundamental processes of nature. Controllability in the realm of quantum mechanics is all about steering a quantum system from an initial state to a desired target state using an external field. Imagine it as guiding a spaceship precisely through the cosmos to reach a specific star. This process is known as state-to-state control. However, the concept extends further to controlling multiple states simultaneously, effectively managing a unitary transformation. This lays the groundwork for quantum gate operations, crucial for quantum computing. The foundational work on the controllability of closed quantum systems was pioneered by Tarn and Clark. Their theorem, rooted in control theory, states that for a finite-dimensional closed quantum system, complete control is achievable. In simpler terms, any arbitrary unitary transformation of the system can be realized with the right application of controls. This complete controllability implies that state-to-state transformations are possible. However, finding the precise control field for a specific state-to-state transformation is no easy task. The complexity of this computational challenge increases dramatically with the size of the system. It's akin to solving a massive jigsaw puzzle where each piece must fit perfectly without disrupting others. The algorithmic task of generating a unitary transformation scales factorially with system size, making it a high-complexity problem. Interestingly, solving general quantum optimal control problems is equivalent to solving Diophantine equations, a class of problems known for their computational difficulty. In fact, it follows from the negative answer to Hilbert's 10th problem that quantum optimal controllability is, in general, undecidable. But the challenges don't end there. When constraints are imposed, controllability can be significantly degraded. For instance, one might ask, what is the minimum time required to achieve a control objective? This concept is known as the quantum speed limit. By quantizing Ulam's control conjecture, scientists can calculate this speed limit, adding another layer of complexity to the puzzle. Now that we've navigated the complexities and challenges of controllability in quantum mechanics, let's shift our focus to constructive approaches to coherent control. These methods offer practical solutions to the daunting problems we previously discussed. The constructive approach uses a set of predetermined control fields for which the control outcome can be inferred, making the process more manageable. One classic example in the time domain is the pump-dump scheme. This method involves an initial pump pulse to excite the system and a subsequent dump pulse to drive it to the desired state. In the frequency domain, the 3 versus 1 photon interference scheme stands out as another elegant solution. Another constructive approach leverages adiabatic ideas. The most well-studied method in this category is stimulated Raman adiabatic passage, or STIRAP. This technique employs an auxiliary state to achieve complete state-to-state population transfer, ensuring high fidelity in the control process. Among the various pulse shapes, chirped pulses, pulses with a varying frequency over time, are particularly prolific. These pulses can be finely tuned to match the specific requirements of the quantum system, making them a versatile tool in the arsenal of quantum control. By employing these constructive approaches, scientists can navigate the intricate landscape of quantum mechanics with greater precision and confidence. These methods not only simplify the control process but also open new avenues for research and application, particularly in quantum computing and advanced quantum technologies. After delving into the constructive approaches to coherent control, let's explore some of the fascinating applications of these techniques across various scientific fields. Coherent control has a wide array of applications. One key application is in molecular and bimolecular chemical reactions, where precise control over reaction pathways can lead to more efficient and targeted chemical processes. Another notable application is in the biological photoisomerization of retinal, a process essential for vision. In the field of nuclear magnetic resonance, coherent control techniques enhance the resolution and accuracy of spectroscopic measurements. In the realm of ultracold matter, these methods are used for photoassociation, allowing for the creation of novel molecular structures at near absolute zero temperatures. Quantum information processing is another area where coherent control plays a pivotal role. By manipulating quantum bits with high precision, scientists are paving the way for the next generation of computational technologies. Attosecond physics, which deals with phenomena occurring on the attosecond timescale, also benefits from coherent control. These ultra-fast processes allow for the observation and manipulation of electron dynamics in real time. An important consideration in coherent control is the spectral selectivity of two-photon processes. These concepts are applied in single-pulse Raman spectroscopy and microscopy, enabling detailed analysis of molecular structures. As a cornerstone for enabling quantum technologies, optimal quantum control continues to evolve, expanding into diverse areas such as quantum-enhanced sensing, manipulation of single spins, photons or atoms, optical spectroscopy, photochemistry, magnetic resonance, quantum information processing, and quantum simulation. By leveraging these advanced techniques, scientists are not only pushing the boundaries of our understanding, but also opening up new possibilities for technological innovation. Thank you for joining us in this exploration of the myriad applications of coherent control. If you found this journey enlightening, don't forget to like, subscribe, and hit that notification bell for more captivating insights into the quantum world. Until next time, keep questioning and exploring.